Okay, welcome back to another video lecture for Math 1316, Plane Trigonometry. And in this video lecture, we are going to be proving the sum and difference identities for sine and cosine using Euler's formula from the previous supplemental video lecture. Okay. So to begin with, let's write down what Euler's formula says. It says the cosine of theta plus I times the sine of theta is precisely e to the I theta. Next, we'd like to consider that the argument in this particular expression is going to be a sum of two different angles. Meaning, let's write this as the cosine of A plus B plus I sine of A plus B. And from Euler's formula, we know that this is going to be equal to e to the power I of A plus B. Okay. Well, notice that the right-hand side of this is an exponential, and I have an exponential. If you were to distribute the I through this, we'd have e to the power IA and e to the power IB being multiplied together, which is equivalent to the previous part of this. But then notice that we're allowed to express anything in the form e to the IA as a cosine plus I sine theta sum. Okay, so we have here the cosine of A plus I sine of A and the cosine of B plus I sine of B. And that's just applying Euler's formula backwards so that e to the IA becomes this and e to the IB becomes this. Next, we can notice that these are two binomials multiplied together. So multiplying cosine A and cosine B, I'll get cosine A, cosine B, plus then I'll have cosine A times I sine of B. So that is I cosine A sine B plus, and I've done this one so far, and I've done this one so far. So then we want to multiply I sine of A times cosine of B. So we will have I sine of A cosine of B. And then we'll multiply the last one, which is going to be minus, because we have two i's there. I squared is -1, sine of A sine of B. But if I collect everything over here, we can notice that the real part of this expression right here is going to be cosine of A cosine of B minus sine of A sine of B, and that's the real part of this expression. So that must be what cosine of A plus B is equal to, because this is the real part of this expression. And the imaginary part of this expression will be sine of A cosine of B plus cosine of A sine of B. And that's equal to our e to the I A plus B. And then by comparing coefficients here, we can notice that the real part matches the real part and the imaginary part matches the imaginary part. So that lets us write the actual identity. That is that the cosine of A plus B will be precisely the cosine of A cosine of B minus sine of A sine of B, and that the sine of A plus B will be precisely the sine of A cosine B plus, and then we'll have the cosine of A sine of B, and those are the results. Okay, so a couple of notes here. Notice that the cosine identities, we can do a similar thing where we do A minus B. in which case we actually get one thing over the other here, and then the proof works pretty much the exact same way. But we notice that the cosine of a plus b, when we have a sum or difference involving cosine, then the cosines of a and b are together, and the sines of a and b are together, but that the operator in the middle of those two terms, cosine a, cosine b, and sine a, sine b, will be the opposite of what we see in the argument. So if this is a plus, that's a minus, and if that's a minus, that's a plus. So we can see that when we plug in a minus, then we actually get the opposite thing right here. Now, sine of a and a plus b, on the other hand, we see that the sine of a and cosine of b are together, and then we have the cosine of a, sine of b together. So the sines and cosines are like mixed up, but we can see that the sign in the middle agrees with whatever the sign in the argument is. So when I do a minus sign here, I get a minus sign there. When I do a plus sign here, I get a plus sign there. And there are the sum and difference identities for the sine and cosine trig functions. Okay. So far, we have that the sine, a plus b, involves mixed up sines and cosines, but that it agrees with whatever the symbol in the argument is. And we have that the cosine of a plus b, or a minus b, has where the cosines are first and the cosines are together. And then we also have that the sines come second and that they are together, but the sign in the middle does the opposite of whatever the symbol in the argument was. Okay. So this is particularly important because we may be asked for some values of things that are not on the unit circle. How do these get used? Well, example, let's suppose that we have the cosine of 75 degrees. All right, we'll notice that we can write this as the cosine of 30 plus 45, because 30 and 45 will make 75. Well, we have unit circle values for the cosine of 30, and we have unit circle values for the cosine of 45, and so this allows us to use our identity for the cosine, which is that the cosine of a plus b will be cosine of a cosine of b minus sine of a sine of b. So we'll have the cosine of 30 cosine of 40 minus sine of 30 sine of 45. But now we can just plug values from the unit circle in. The cosine of 30 is square root 3 over 2, and the cosine of 45 is square root 2 over 2, minus, then we'll have the sine of 30, which is half, times the sine of 45, which is square root 2 over 2. And notice that we have something very simple now. This will be square root of 6 over 4. And then this will be square root of 2 over 4. So we get that our final value for the cosine of 75 is square root 6 minus square root 2 all over 4, and that's it. And this is a value we wouldn't normally be able to compute because it is not on the unit circle. So with the sum and difference identities, any number that can be created using 30, 45, 60, 90, 120, 135, the numbers that appear on the unit circle, we now have a way to compute their exact sines and cosines. Second example, what if we were given, and this is actually an ACT problem from 2001, I want to say, where we have like the cosine of 173 cosine of 83, and then we have plus sine 173 sine of 83. We'll notice that this is precisely one of our sum or difference identities. When the cosines are together, that tells us this is the same thing as cosine of something. And then it will actually be the opposite of whatever this symbol is here in the argument. So we'll have 173 minus 83, which is the same thing as writing the cosine of 90 degrees, because 173 minus 83 will end up being 90. Okay, but the cosine of 90 degrees is just 0. So we can see very clearly that we're able to go both forwards and backwards using these sum and difference identities. Now, the second part of this is actually something that we talked about in an earlier section. They are the cofunction identities. Remember, the cofunction identities are like sines and cosines and their relationship to one another on the right triangle, which is that the sine of capital A is just the same thing as the cosine of capital B, and vice versa. So the cosine of A is the same as the sine of capital B. Well, because of that, we can also derive that the tangent of A is the same thing as the cotangent of capital B, and the cotangent of capital A is the same as the tangent of capital B. Next, we have that the secant of capital A is the cosecant of capital B, and we have that the cosecant of capital A is secant of capital B. And the relationship there is that all of these things are related by the complement of the argument. So if you have the sine of 30, this is equivalent to the cosine of 60, because 60 and 30 are complements of each other, and sine and cosine are cofunctions of one another. And those get used a lot in constructive proofs, but you'll be asked to rewrite these. And we've actually seen these before, so I'm not going to go very far in depth with this. But the major thing here is that we can actually use these sum and difference identities and these co-function identities in constructive proofs. And that is that we have, say, the secant of I plus x equal to negative secant of x. So let's verify that this identity is true. Now that we know the sum and difference identities, we add to our checklist from section 5.2, and we kind of go through the same motions as always. But we'd like to work with the more complicated side, if at all possible. That would be this. We have an option here of noting either through the cofunction identities or the sum and difference identities, but I think the more like direct, obvious way, even though it's definitely not the most efficient, but the most direct and obvious way to me is just to go ahead and to try to apply a reciprocal formula so that this becomes cosine. And then what we're going to try to do is use one of these sum and difference formulas to get this thing down to where we have just negative secant of x. So we can notice that secant is just 1 over the cosine of pi plus x. And then we can apply a sum and difference formula where this is a and this is b. So we'll have 1 over, and our sum and difference formula says we'll have the cosine of pi times the cosine of x. And then this was plus, so we'll have a minus here. Then we'll have the sine of pi times the sine of x. But notice that the cosine of pi is just negative 1, and the sine of pi is just 0. So if I take the sine of pi, that term goes to 0, leaving me with 1 over cosine of pi cosine of x. Cosine of pi is just a negative symbol. So 1 over negative cosine of x is precisely secant of x negative, which is negative secant of x, which we were required to show in the first place. So you can see that now that we have sum and difference identities, we have the ability to prove some additional identities or verify additional trigonometric identities that involve changes to the argument as opposed to just the trig functions that are like multiplied or divided or added or subtracted to each other. Now we can actually show that things are true when the argument of the trig functions have changed. So 5.3 will be quite a few just very easy plug it in sort of examples, verifying that you know how to use the sum and difference identities for sine and cosine. And then you will be asked to prove a few things about the different types of identities that can be derived in this way. Now notice also here that we had the pi is effectively 180 degrees plus x. So first of all, if I do the co-function identities here, then what I could do is I could recognize that this is like 90 minus x twice. It's just like in the reversed order here. So if I do x minus 90 or vice versa, knowing that secant is an even function, and so if it works out to be negative, it doesn't matter. It's the same thing as a positive secant. Then this would be like 90 minus x twice. So it'll turn into secant in one direction, and then it will turn into cosecant in one direction, and it will turn back into secant in this direction. And it's just that it's got this negative symbol out in front of it, which we'll get from the cosecant, which is an odd function. So then we'll have to factor something out. The negative goes out in front of it because it's odd, and it turns back into secant. That's like the more tricky but more efficient way to prove this. I'm not going to write it down. I encourage you to try that if you're interested in it. Just note that you're going to have to like factor a negative out of the argument here, and then this will turn into cosecant. A negative will come outside, and then it will turn back into secant with just x instead of having something in the middle. So I encourage you to try that proof or look it up if you're interested in that kind of thing. Okay, so if you understand that, then you understand section 5.3.